So good evening, everyone. We will be starting now. I think many of you are already here. 34 are here. So remaining of you guys, remaining will keep on joining. So thank you again. I see your schedule is packed and still you guys are having full enthusiasm to have these courses, and that's so nice. Very inspiring for us as well. So let's start today's class. Today's class will be again on the phase module 1 of the computer applications, where we are talking about the algorithms, flowcharts. Today we'll be also introducing the programming aspect and how programs come into picture. So till now we were learning about what are flowcharts, what are algorithms, what are the differences, how one can be converted into another, right? What are the different parts of a flowchart? What are the different components of a flowchart? And we also, I think, many of you or most of you have started working on the assignment you have, and I think uh, Swati has already submitted, I think, her first draft. So try to keep on working on that, and also even Swati, everyone. Today, what we will also be discussing are some of the common mistakes we do in algorithms. So let's start with that. So common errors while making flowcharts. So very small mistakes that we sometimes do that we can take care of. So we will be discussing those. Then we will be also talking about now from today how these flowcharts and algorithms translate to a program. Now, the whole purpose of flowcharts and algorithms is basically to understand and make a plan to move on to the next part, which is the development of the program, right? So, how programming comes up, what are the differences, how things change uh, when we transfer from algorithm to a program, what are the basic components of a program, what has to be taken care of while writing a program, some things, and maybe some examples we'll see and problems we'll solve if time permits. So we'll see about that. So last time we saw flowcharts. We saw how basic they are and how very informative they are. Uh, we have definite shapes which depict definite work that is done in that step. We have definite direction in which the process moves, and the information that is relevant is provided in that. So very by just seeing the flowchart, we can have an idea where the process is going and where it will terminate, what are the steps involved, where there will be inputs, where there will be outputs, and where the processing is going on. So that's the first step to basically solve any problem. If we have, suppose, a problem where we want to install an air conditioner inside the house. So if in that case we have to first find out what are the things have to get, go to the shop, purchase the AC, get it in your house. Now the processing part may be to plan where the AC has to be installed, to basically do the fitting work, to the installation work, maybe get a new air conditioner line of powers because it requires more power, and so on. So many steps can be there of processes, and finally we get the cool air or the air conditioner is installed. That is the final output. So each and every problem that we try to solve or we see in day-to-day basis can be basically differentiated in terms of these stages or process, we can say different sections of work, which can include inputs, which can include processing, which can include some conditions, which can include some repetitive works like loops we saw, and which can get some output out of that. So we saw how to make flowcharts. We also did some exercise in our lab as well. which was quite short if we see in retrospect, but I think you got the idea how things were done. So just to also maybe continue with what we were doing, and what are the some of the common problems, common errors that we generally make when we make a flowchart. So there are some very basic, but in principle important aspects where we can improve or can make processes perfect in a flowchart, or more representative or less ambiguous in that sense. So first, coming to that, one of the major was simply use of appropriate symbols. Now in this flowchart, I am trying to input two numbers. Again, the same thing, finding the maximum output, right, of the two numbers. Can someone tell me where have I made a mistake? Anyone? Which is there any mistake? Yes, Amritesh?
So print max.
Print max. So what is the mistake here?
So it should be parallelogram.
It should be a parallelogram. That is correct, because any input and output operations that are done, or any interactions, such interactions that are done, that should be in a parallelogram. So see, each and every box is a process. That is true. And it's always our feeling that, okay, let's put a process box here, so that will work. But the whole point of flowchart is to understand how things are going, which part is doing what. And so we need to take care where the input and output operations are going on. Similarly, we have to understand which are the processes. It should not be that we, in place of decision, we put a process box, or in place of process box, we put an input output. So each and every symbol has its own work. So try to keep that in mind. And when you make flowcharts and when you do assignments, do keep in mind that as well. Okay. Inconsistent flow directions. Now you see this set of process. It goes from cloud forms to rainfalls, and it has two subdivisions: a lake fills and a river flows. Now the thing is, there may be many conditions in which multiple actions happen after a single step. Suppose there is like a pandemic is there. So pandemic is there. So there will be sickness that is spreading. There will be hospitals that will be preparing for that sickness, or they will be preparing for the ventilators, or the beds for the patients. And there, in parallel, there will be vaccines developing. There will so many steps will be going on in parallel to any process. So this condition will happen, that okay, after rain falls, lake will also fill and rivers will also flow. But what for a flow chart to be properly demonstrating what is going to happen, it has to have either a decision in which it decides, okay, these are the ways, this is the way I go if this is the condition, like if an else statement is there, or it should be a post distributed process, like if these two came out below the lakes, or due to after some other process, in a unidirectional way. In that sense, that after rain falls, it will happen that more processes will happen, but in a chronological order. So that's an important thing that flowchart has to cover. So consistency in flow direction has to be maintained. Sometimes that happens that so many things are done in parallel, so we forget how to do that. But that we have to take care. Okay. Scaling of text. Sometimes text is becoming very small or very large. Symbols are very small that they don't hold full text, or they are very far away as compared to what we are trying to do. So take take proper care of how to scale the text so that it is visible properly when you have a glance of a flowchart overall. Uh, Take care that the box is not very big or very small, that it doesn't hold what you want to show. And take care that overall spacing and text size are proper. Okay. Forgetting the arrows, very common. If we don't put the arrows where the flow is, we can't show. And the name of the activity is flow chart. So flow is very important to be demonstrated. So don't forget the arrows. Even though it may look that, okay, this is the way it should work, it may not be necessary that it is the direction we intend it to be. So arrows are important. Okay. Connecting other to other pages. Now this is very, as I think I described a bit, but not in detail. So using connectors is very important and very essential when we go for large flowcharts, especially those which do not come in one page. Like if you see here, they have used a connector called and named it as B. Now the no condition will have another flowchart that will start with a connector called B. This is the way we manage large flowcharts. It can be, these kind of connectors can be in the same page, or there are other connectors that connect the flowcharts in a different page as well. So as per our application, as per our requirement, if we are making different pages, or just we are making same page, different flowcharts parallelly, or one after the other, as per our requirement, we can do that. But using connectors becomes important if in order to make the flowchart visually appealing and visually clear, and not basically congesting the components so as to make it unclear. I'll give you a very show you a very nice example, which actually I only made for a flowchart while I was working in a company, in my previous company. So after this, I will show how many mistakes I had to do in order to accomplish something. Okay, infinite loops. This is clear. We were discussing that day as well that we have to take care that loops are finite. Infinite loop basically means that something is wrong, or we have made an error in planning the process. So do take care of that loops are not infinite, conditions are met, and the amount of detailing that is required. So we can write big statements inside the flowchart. We can write small statements inside the flowcharts as per our requirement. However, it is always preferred to be concise. It is always preferred to be on point what we want to say. It should not be that five amount of numbers were asked by the user, asked to the user to be inputted. We can just replace it by input 5 numbers, something like those. There can be many other conditions. So be precise, be to the point as much, write as much as required, but uh, as less as required as well. So amount of detailing is a point here, important. And now I want to show what the example that I was talking about. So this is a flowchart that we basically developed for slope stabilization work, or deciding for a slope stabilization work what to do, how to proceed, if we get a project what to do, and so on. So what I will do is I will just run it through with you guys, and do keep noting what are the problem areas. So your work will be to keep on noting where I made a mistake in terms of what we discussed just now in terms of regular mistakes and all, and what improvement could have been done in this. Okay, so starting with the, I may started with a slope stabilization terminator. So I just wrote that it basically describing the slope stabilization work. So first we were getting briefed by of the problem. So what usually happens in our setting was being a technical senior technical manager there. So my profile basically needed me to deal with the problems, give the solutions, and suggest what will be the best possible way or best possible application for slope stabilization work. So the work for getting new projects, like where the slope stabilization is a problem, or who is the client, what is the problem, these all things, a sales team or the marketing person used to do. So this flowchart is basically for what I used to work as a technical manager. So what my work profile required me to do. So that I had to make for that. So first step was get briefed about the problem from the sales team that I used as an input. Then obtain the reports that are available for that project, again from the sales team or through the sales team. Then there was a decision, is the assessment form available for this? So what our practice was, we used to give each and every company or any project we used to give a assessment form. Okay, you fill the assessment form. Assessment form used to have very generic details of where is the location, what from when there is a issue and what kind of issue is there you have noted, or what are the slopes and how tall it is, or what are the factors, is the geotechnical report available, is the rock mechanics test done, if not done, can you arrange or would you like us to do it, and so on. So many parameters were there, yes, no answers were there. So assessment form basically gives an idea of what is the situation practically, and associated to the assessment form there were very many reports, so that we at least get an idea of what the problem is, where the slope stabilization work was required. So, so is the assessment form available for this problem? If yes, then supply the assessment form to the sales team to be filled from the client, get updated report and data. Okay. So if assessment form was there, give it to the sales team so that they can give it to the client. If not there, then make assessment form for this issue. So it was not just slope stabilization. There were many kinds of slope stabilization that was different scenarios were there. So for each scenario, we had to make a new assessment form because many of the relevant condition in one slope may not be there in another slope. Like in the mining slope, we asked for what is the bench angle, what is the bench height, what is the berm width, what is the type of mineral excavated, what are the excavators dimensions, or and so forth. These things we cannot ask to client on the civil side. So assessment forms were made on the basis of what kind of problem we at least know from the first contact. Then we used to supply them, we used to get them filled. So after supplying the assessment form, get the updated data. Now analyze the report. So this is in process form. Analyze the report and the data available and refer list. So now I have put a list here. And what is on the list? There is so much data here, but that I have put in a document format. This is a symbol where you can store a document or a data, something like that. So exact location, what are the sectional profiles, extent of instability, pics and videos if available, type of rock, UCS, tensile, Poisson's ratio, Young's modulus, all the rock mechanical properties were asked, RMR, RQD, type of soil, all the rock mechanical and geotechnical properties were asked. Then there was geological log encompassing if the geological survey was done, section map, previous history of the region. So hydrological properties, rainfall, which all the factors that we were just discussing, seismic data. So all the factors that we were just discussing in our slope stabilization process. So we used to mostly ask for these parameters. And or more than 90% or 95% people didn't used to have almost all of it. So they didn't used to have any of these reports or any of these because uh, see these are not the priority for a person who is working on a field because they have to basically have to extract or construct. So they may have very basic idea of what things are, but especially when the situation is slope stabilization or a ground improvement problem, so they don't have too much data that we actually need to fully understand the situation. But it's our job to ask because we can't assume everything. So after we refer this list and analyze the reports, we see a decision again. Is the data sufficient for the analysis and design and methodology formation? See, analysis, design, and methodology formation, these were the three parts. So if yes, so is the site visit required now? So in case when the data is sufficient, we have to ask if the site visit is required after this. If it is not, then we proceed to some other way that will be moving later. If it is required, then we conduct, arrange, field visit, observe and analyze, refer list, and we also have a list where we see what all we have to do when we do a slope stabilization field visit. So when we do a slope stabilization field visit, we assess the data, observe the location, slope movement, cracks are there, what kind of rock soils are there, pics, we take pics, very important. Rock soil sample collection, if we can collect the samples. Any other data that can be collected from the site because site offices have many data, but they are very lethargic basically to find it out. So when you visit site, you can actually press those guys to find the data that is required. So that is there. So this goes to conduct, arrange, field visit, and conduct that. Another process when if data is not sufficient, the no part of it was, can it be obtained from the client? If it can be obtained from the client, the decision, yes, request for missing data, right? If no, can they be obtained by sample laboratory testing if laboratory testing is required or not? So you see how much nesting of if then and then statements are going on. Yeah, is the data sufficient? If not, can it be obtained? If not, can they be obtained from sample laboratory? And if not, can estimates be made via other resources? So all these considerations were there. So let's take it maybe slowly now. Can they be obtained by sample laboratory testing? So if client is not able to provide the data, we ask for laboratory testing. If laboratory testing can be done to get that data. If it is yes, then for that also, do we require to visit site for sample correction? If yes, then again go to that process, the site visit process. And if not, then arrange for the testing of samples with labs and obtain the test results, correct? Okay, and if they cannot be obtained from the sample laboratory testing, what happens is, this is the condition that can estimates be made via other resources. Other resources can be, maybe we can go for the internet resources or we can go for the previous world projects or something like that. If yes, then we go to the main process of working. If no, then you see where it is going. Project can't progress without the required data and we reject the project. That was sometimes we had to do that because the client was very maybe not willing to give data too much or didn't have data but didn't want to spend too much money. So things happen, so many things happen. In this decision, what client wanted, can it be obtained from the client? Can the missing data be obtained from the client? So if it can be, so request and we go to back to the loop because we have to basically analyze if everything is properly done or not. Moving on, after the maybe possible field visits, maybe lab results and any other sources, we move to the process to make preparation for simulations. including profile extraction from reports, sections, conversion of appropriate DXF, and so on. So basically, when you will be we'll be learning in both of these classes how slope stability analysis will be done. So in that we require for two-dimensional analysis, we require some sections to be obtained, the cross-sectional profiles, how deep it is. As we were discussing in one of the examples today in rock slope technology, what is the depth, what is the height, and so on. So these all things are required. Then material properties, obviously, we try to find from the other reports as well. So material properties, DXFs, basically cross-section profiles and all, we obtain. We simulate in actual conditions with all properties. Okay, and we see, are the FOS values unexpectedly high or low compared to site conditions? Now we had already visited, or we have sufficient data to basically understand what is the site condition. So are the values of factor of safety unexpectedly high or low? If yes, we have to adjust material property. So this is called basically back analysis or follow-up adjustments. So what is at the field? First, we have to match in our simulations. So unless and until we bring our simulations to the level which are exactly representing the field, we cannot rely on our simulations as well. So first thing is always in simulations that we match the present field conditions with what we simulated. If those are matching, then we can simulate other scenarios, like if we maybe go for some stabilization work like bolting. So what will be the factor of safety increase, or if the rainfall happens and saturation happens, then what happens, so and so on. So so adjustment of the model, the simulation model, is mostly done. This is called verification of the model. So verification of the model is mostly done in the first step of the simulation work to represent the field condition, and then we go for basically further simulations to understand what is going on. So if factor safety values are not unexpectedly high or low, and it is close to what we see in the field, we introduce supports and other modifications as required, resimulate, and what we keep as factor of safety is generally 1.5 for our cases. But again, as I said in our lecture, it is different from different cases. So we try to bring the factor of safety up by introducing different supports. See the requirement for surfacial erosion. Now, apart from slope stabilization, we also used to see surfacial erosion problems. As I said, the surface also has to be taken care of. Then we go for estimate quantities based on the design, how much quantities will be required, final detail, and make proposed design based on simulation work. Discuss with the sales team as to what extent data they want to supply. So when we simulate and we have every data, how things will work, generally these application or consultancy firms have to withhold some data before they can get the contract, so that it's not that they give away everything on the first go. They give some data. Okay, this is our design, this is what we have to do, and this will be the factor of safety after improvement. And once they get the contract, they give actual details. Okay, this is the type of bolt we will be using, this is the spacing between the bolting, this is the depth of the bolting we will do, or this is the type of bolts we'll use, and so on, type of geofibers, geofabric, so many things are there, right? Then make a draft methodology as requested. As per sales team, in consultation with sales team, will make a draft methodology. So that report making, like every one of you will be doing some sort of reports while your projects will be decided. So similar reports we have to make for all type of work. So what are the parts of those reports, that also I have to include in this document. and supply the design quantities methodology to costing and sales team. My work was done by doing to the sales team, and that's it for now before the application work. So you saw such a big flow chart. This is a kind of flowchart we can make once we have some complex set of process that we have to follow. So I had gone through one by one. So now I would ask you guys, what do you think, as we had discussed just now, what are the different problems or the different mistakes we can make? What do you think, is this quite a good flowchart, or does this have some improvements or mistakes that can be rectified? Any comments, any observations that you had throughout this? Why I was taking the slope stabilization problem was because you guys are all in slope stabilization as well, so some idea how things will be done is also there. So yeah, please, someone, what do you think? Is this flowchart proper? Is this appropriately done, properly managed, or is there some mistakes that have to be dealt with, or some improvements that can be done? Yeah, please, someone. There are, I would say.
Excuse me, sir.
Yes, who is this?
Sir, this is Prabhu, sir.
Okay, yeah, Prabhu, but
Hello.
yes, tell.
Sir, this
Yeah.
is Prabhu Prasad Raut.
Yes, Prabhu, tell me.
Sir, I think, yeah. Sir, I think this flowchart seems to be a bit clumsy in a single paper. This can be adjusted over 2 or more papers. That is what I can observe.
Very nice. One of the points we were discussing while we were talking about the mistakes was the use of connectors. So the use of connectors could have been done here very easily, right? Like you see, there are two different directions in which this flowchart is moving. First, it is moving down, and then it has to move up, just because it had to basically accommodate in one chart. So my challenge basically that time was I had to make just one sheet. That was one of my challenge. So yes, properly, if we make a proper flowchart, we have to use connectors, and we have to use it so that most of the time we prefer that the flowchart movement direction is in one direction. If we are moving from top to bottom, we keep on moving from top to bottom in the next flowchart as well, and the next flowchart as well, and so on. If we're moving from left to right, we keep on moving from left to right, and so on. So that's general practice. But yeah, sometimes some challenges are there. Okay, any other thing? That was nice, Prabhu. Very good.
Sir, hello,
Yes.
sir.
Yeah.
Sir, something that we can do it. We can abbreviate the language.
Yeah,
That
exactly.
obtain the report available. We can write report available. That's we can do it.
Right. Right. So precision in data, what we put, how much details we have to put, that is very nicely captured by Nitesh. Uh, in this, we had put a lot of details that may have been given in some other way possible, because we basically see we have used like 3 documents that are like almost ineligible if we see in 100% size. So we can't read actually these small text even when we go for actual size. And this kind, even though this gives a lot of information, but it is not very pleasing to basically present in front of someone. Uh, However, yeah, again, conditions are there. This was a task that I had to make basically uh, as detailed as possible and as less as possible. So whatever I could, I did. But yes, uh, there are many places where things could have been precised, obtain the reports available, obtain reports, is assessment form available for this problem. So many things are so much like sentenced, they can be reduced basically. So when overall this reduction is there, the conciseness is there, the beauty of the flowchart also improves. Any other thing? Any other thing someone observed? Anyone can comment? Yes, Swati.
So the arrows, I think they can be more aligned so that one can easily connect that where are we leading to in the next step.
Perfect. Because so many wavy lines are there, and the arrows are actually very small. If you see to the whole
Yes.
picture, it is hardly we can see what is the direction if we don't, squeeze our eyes very much. So yes, that is perfectly captured. The arrow sizes, the thickness of the lines, even the yes no statements. I think I actually edited this one later on, but the first draft actually yes no was so small that I couldn't see which was the yes and which was the no. I think this is the edited one where I changed that. But yes, that is also one of the factors that we have to take care. Okay, I think quite good observations you guys have. And these are the see it is precise. You can print this in one page and paste it somewhere to just basically let anyone who comes in my place or who is doing similar work that I am doing, he can basically refer it very quickly and see, okay, I have missed this or I have not done this or whatever. But in a professional flowchart setting, especially when we are dealing with a program or a programming language, we have to be very clear in our work. We have to be following a set pattern so that uh, even the visually it is okay, as well as understanding wise it is correct. So yes, in challenging situations, things can be bent. Uh, this the dual direction of the movement of the flowchart is never recommended in any place. With that, I had done. So that is one of the biggest catch that Prabhu said. And yes, data and as well as the thickness of the arrows, the clarity, these all things can be improved. And uh, otherwise, it's a good enough flowchart to give a big description of how things are done in a company. But yes, things can be improved, and that's what, as engineers, we have to keep on seeing. Our work is not perfect, and every time there is a room for improvement where we can find out some ways to basically better ourselves, and that's what we have to aim for. On that note, I will give you 2 minutes. If you have any questions, you can ask. If you have any doubts, or just take 2 minutes break, because I know you have been continuously working from like 1 o'clock or 1:15. And then we will move on to them some introduction of how programs are there. Okay, 1 minute now. Yes, any questions? Chintan, yes, Chintan.
Sir, actually, we are adding a lot of text in our flowchart, right?
Right.
So, if we could, we make some smallest form of that text, and we could refer the different another text file, index file like that. So it will be easy to read, right?
Right. Uh, the proper way to do that is actually what you say it is. Actually, I have closed that file, so later on. But the details that I showed you now in maybe I will open it up very quickly again. So the details that I gave in this file actually are a part of many reports that we make, many type of data we get, and these all details are actually in most of the flowcharts. You won't see these kind of detailing done in any of these flowcharts. And again, that's a thing that that is our call that we have to make, how much or how less we can write so that our purpose is solved basically. Uh, Sometimes we have to give details, and there are other ways to give it. Actually, we could have attached a next paper, or use of connectors is one of the best things to do in this case. Maybe we could have used a connector in place of such big texts, right? those could have been done. The steps could have been many places that could have been improved. I would just say in not in defense but in explanation that again the whole exercise was to basically put it in one paper and as much details as possible so that no one has to refer anything else. Still, it could have been improved in one paper itself, but yeah, that is correct. So that too much details in this flowchart are not that much required and can be given in some other ways, some other connectors, maybe some other files. That is true. Thank you, Chintan. Okay, so now what we will do is we'll move on. We have 15 minutes and yeah. So let's now come to fresh topic. How these all things, flowcharts and algorithms, translate to a program. Now we have seen that how an algorithm can be converted into program. You guys are doing that as an exercise as well. However, that's not our purpose right now, because that's just a step in the direction of making a full-fledged work that we have to do. So next what we do is write a program. Now here also this program is the same program for finding maximum among two numbers. This code is written in MATLAB. Now when we talk about a code, now we are becoming very specific in terms of what language we are using, because each and every code that we write is different for each and every language that we use, right? For C++, the same actions will be done in different syntaxes, different ways in which it can be written. This, for example, here, many things that are required in other languages are not required in MATLAB, and that's one of the advantages. That's why we will be learning MATLAB here, and we'll be using it in some other modules where artificial intelligence and all will come up. But primarily focusing here, this is how same program that we are seeing here can be written in form of a MATLAB code. So here also you see there are clear sections that are there. The top section you can see is like in the flowchart and algorithm we saw there are different sections of inputs. There are processing, there is control or decision making, and there is output. Similarly here also you can see in this program there are different sections, very specific sections are there. First section is getting the input. So we are getting A1 and A2 as the two variables, right? And in that, now we are comparing secondly, how A1 is greater than A2. If A1 is greater than A2, then assign a value of A1 to another variable that is max. Else max can be A2, similar to the other algorithms we see here or the flowchart we see. And there is a display or the output part where you display the bigger one. The bigger option is and max. So clearly there are all of these have parallels, but in each and every case we represent them differently. Like in algorithm we just put as simple as input number A. In flowchart we put a box, parallelogram box or a specific box that we have to put, and in different codes we write different set of instructions, different maybe an input program like in this case or input statement in case of C++. So let's see, I have I think a program in C++ as well. Yeah, so you see this same program is written now in C++, and just for the sake of comparison you see how very similar these programs are. Even in this we have some inputs in MATLAB. In this we have some inputs in form of I and J. In MATLAB we have the if-else operator. Again in C++ we have this if I is greater than J max. if else max is j. So quite similar in terms of what we want to put, display the output part, and there is a cout function in C++. Different. So it's something that we were talking about. Remember when we had our first lecture was how we call the same object differently in different languages. Like we call apple in English and seb in Hindi or any other thing. So similarly, work that is done in each language is same. However, what it is called in each part is different. Like in MATLAB, the request for inputting any variable is done by a input statement, that is an input function, that a1 equals to input bracket some text that can be given. However, this in C++, there is a different input statement, that is cin, and that is putting the value of I in, putting the value from user into the I variable. So doing the same thing, and having the same solution can be possible from each and every programming language if we understand what is the principle behind. And that's where our flowcharts and algorithm exercise came, was very important. So once we know the principle, once we know the sections that we are making, this is the input we want, this is the processing we want it to do, and this is the output we want. Each and every language is accessible to us as long as we come to know what are its special words for doing the same thing. So now this was the algorithm and this is the program right now. So why are these different? Why is a program different from an algorithm? And what specifically differentiates between them is the importance of syntax in any language. So syntax means the specific way in which we have to write any work we have to do. Now, input number A as input number A, as we saw in the algorithm, could have been written in any form possible. Like in flowchart, we were writing in any way. You please enter input A, please enter 2 variables or enter 1 variable. But in a program, we can't do that. Program is basically, now we are dealing directly with a computer. Computer doesn't understand everything we say to it, at least programming wise. So in order to let it understand what we want to do, we have to take use of very specific operators, very specific set of words in a specific arrangement. Now this set of specific words in a specific arrangement for doing certain stuff is called a syntax for any work. Like for inputting a variable in C++ in form of I, so that can be done by cin and greater than I and a semicolon. So this is called a syntax. Now we can change anything, any variable in this. We can basically use I, J, K, apple, number 1, number 2, number 3, anything we can do, but the pattern in which we are writing this will remain same for different cases of input. So that is called syntax. And that is where a difference between what we were doing till now, that is algorithm and flowcharts, and what we will be doing now onwards, that is programs, will be different. Now programs, that's why, since syntax is so much important, now the universality of algorithms and flowcharts is not seen in programming or coding, because for each and every language there will be different syntaxes. So for for example, in the same way, on the left is a C++ program we were seeing, and on the right is the MATLAB program. MATLAB code doing the same thing, but if you can see clearly, there are very clear syntax differences in which we can write. Now we know. Let's see what are the what we can see in this program. Now in first let's see MATLAB. MATLAB we see there is a PR equals to some text that is written, please enter first number, PR2 equals to please enter the second number. And what we are doing is we are getting some number A1 and we are giving this PR that we stored here, the full text that we stored inside PR, we are giving this in a function input and we will get some user input from that will be stored in A1. Similarly for A2, that will be there. In C++, similar thing is going on, but they have to use different things for basically printing and different thing for inputting. So cout is a output statement in in C++. Cin is the input statement in C++. So cout basically gives what we want to put on a screen, what we want to put on terminal, what we want to print simply on the screen. There are other functions as well. There are other statements of output as that printf is there. There are many other ways that we can do in different languages. Even in C++ we can do in different ways, but one of them is this cout. And for inputting the value I, we do cin. Similarly, if we see the next part, so this was input output. If we see the next part, the if statement. So in MATLAB, if we see if A1 is greater than A2, max is equals to A1, else max is equals to A2, and we have to end it here. In C++, it's very similar. If I is greater than J, max is this, else max is J. But there is no end required here because C++ has a different way of compiling its code. After every line, it has a line number, and it can basically see how much is the scope of this else statement, or how much is the scope of this max statement. However, in this MATLAB, we have to put an end below this so that the program knows, okay, this is the end. So that in C++, this has been an issue because sometimes what we do is we don't write the statement just below the else. Maybe we do it after one line, and sometimes else basically skips that and thinks, okay, there is no statement in else and let's continue with the process. So in order to avoid this, so now modern languages also basically encapsulate what we want to do, and that's why this kind of end you will see in modern languages. And again, coming to cout, it's simple. Cout in C++, display what we want to display in MATLAB. So that's quite similar. But apart from these, now MATLAB, we see some other things as well. So in C++, we see this hash include things are there, that is including something, some files maybe. There is some void main type of thing that is there, and there are variables that are used inside, but they are different. They have been basically written before. So these kind of ways, these are actually different components of a single program. And what are these components? These components are specific to very different languages. Now, what I will do is for now, let me not go into the specific components. What are these called? Let me take it later on because already time is up. But what we will do is in next class that we'll be meeting in the CAM lab, I think. We'll be meeting in CAM lab. We will be discussing this further and we will be writing some codes. Now, if you guys Do tell me if you have accessibility to MATLAB with you guys, if you can have access to that. And if not, there is access to it online. So we will see what we can do there. Okay. So we'll stop here for now. We'll be discussing basic components of programming later on. I think your next class also you are waiting. Okay. Okay. Okay, guys. So I'll stop here. If anyone has any questions, you can have, but you can also attend the next class because professor will be waiting for you. And thank you so much for coming again. You guys have been very enthusiastic. I know everyone is very continuously on the monitors, continuously on your laptops, going on with the classes. But your enthusiasm is basically what motivates us to go on. So well done. Keep on going. And thanks, guys. Stay safe. Take care of yourself. Take care of your parents. Take care of everyone around you. Okay. Thank you.
Excuse me, sir.
Yes.
Sir, can I edit my assignment a bit?
Yes, sure. That's why I wanted this class to be before the submission deadline.
And sir, will the 2014 MATLAB version work, or should I?
I think it should work. I think because we are doing the basic programming only. So because complex programming is not there, so it should work. But what kind of license do you have? A crack license, or do you have a institute? Crack is there?
No, I actually, yeah, I downloaded it from a site. So
That's okay. For now, we can work it out. But when we do some bigger modules like artificial intelligence, all things, I think you will need some updates. So let's see when we reach that bridge, we'll cross it. So for now, it will work. So we'll all meet on Thursday then. Okay.
thank you, sir.
Okay. Thank you, guys. Thank you so much.